Hi everyone. I want to walk through a couple of problems about the more extended Frobenius theory and what these things look like in practice. One of these questions came up in office hours and I ran into trouble when I was trying to solve it, and then I didn't really have a handle on the best way to explain it until I wrote it all out. So hopefully this sort of step-by-step guide to attacking this question will help those of you that are maybe a bit overwhelmed by the technical density of the Frobenius theory stuff. It's not so bad. So we're going to work at problem 14, and problem 14 obviously is of the form so that it has a regular singular point at 0, like all the Frobenius problems do. And you can tell because this is P and this is Q, and those are both analytic everywhere. And so that means that we're going to assume that our solution has the form of a Frobenius series. The way we do these questions is the first thing we do is we find the R values that are going to guide what our Frobenius series look like. And we're going to do that by finding the index equation. So we need P0 and Q0, and that's easy enough to find because they're right here and right here. So P0 and Q0 are both 6. Another thing I'd like to point out, just to remind you, because it's going to be important, is that P and Q are both power series. They're just power series with a finite number of non-zero terms. In fact, that's all a polynomial is. Okay. So there's one approach to this problem that is going to require that you know that. We're not going to see that in the way we're doing it, but it's still an important thing to note. Okay, so the next thing to note is that when you plug all that in to the index equation, you get these as your roots. And those roots are in the problem case for distinct real solutions because they differ by an integer. And the important thing to note is that the actual integer they differ by is going to be the problem point in the second solution. So what I mean by that is there's going to be a trouble point, and it's going to be the coefficient b1. When we get all the way down to the bottom with the second solution, if the recursion works for b1, then we're okay. And if it doesn't work for b1, then we're going to have to do something different. Okay? From here, the process is pretty similar to the usual process. We're going to find the recurrence relation by plugging in the Frobenius series and its derivatives into the differential equation. When we do that, we end up with a pretty typical series representation here. I have skipped the step where, at least the algebra step, where I took the x squared and I've already multiplied it in, and I took all of this and I multiplied it in, and I took this and multiplied it in. So these series down here already contain everything multiplied into the series. So there's only one term that we have to deal with where we have to change the power to make it match, and that's this term right here. And so that term we're going to have to shift the index back. The other thing that I'm going to do right now before I move on to the next step is I'm going to factor out and get rid of the x to the r that's in all of the terms because it doesn't matter. X to the r can't be equal to 0 on the interval from 0 to infinity, so I'm allowed to divide it out of the question. So it doesn't affect anything. After you do that, you end up in this situation. And so here, what we're dealing with is, well, now we've got this index, which is 2, and these all start at 0. So we're going to have to peel off the n equals 0 terms and the n equals 1 terms to smash everything together into a single series. So this is the stuff that corresponds to n equals 0. And this is the stuff that corresponds to n equals 1. From here, we can check whatever conditions we have on the series in terms of a0 and a1. We already know that we've picked R values, hopefully, that end up with this thing equal to 0 in both cases. And what do I mean by that? I mean, if you put in, or if you algebraically simplify this, you're going to get R times R minus 1 plus 6R plus 6 is times a0 is equal to 0, but the particular R values that we're going to pick are going to force this expression to turn into a 0. And that means that if 0 a0 is equal to 0, then a0 can be arbitrary. Then we can check the same conditions for a1, and you could multiply this out and simplify, but it doesn't matter because it's actually easier just to check. And then once we know a0 and a1, then we can continue on with this to give us the rest of the recursion. Okay, so we've built out our recursion by peeling out the n equals 0 term and the n equals 1 term, and we smashed everything else together into the sum from 2 to infinity. So this contains all of the rest of it. And what I'm going to do is I'm going to take all of this, and I'm going to set all of that equal to 0, and that will be the recurrence relation that I use to generate all of the rest of the coefficients. Third step of the question. So I'm going to plug in my R1 value, where R1 is the larger of the two distinct values that you got out. R1 in this case is -2. So when you plug that in, I'm just going to check all the conditions. When you plug -2 in to that first equation, so this was equation 1 from right here, and you set that equal to 0, then you end up with after you work this out, you end up with the equation 0 times a naught is equal to 0. And that means that a naught can be arbitrarily chosen, which is perfect because that's what we want. Now we're going to check equation 2, just to verify what's going on with a1. So this is equation 2. Equation 2 says, when you plug your numbers in, that you end up with a non-zero number right here. So you get 2a1 is equal to 0. And of course, that means that a1 is equal to 0. 2 is not equal to 0, so a1 must be. Because of the structure of this recursion, it means that a1 is going to force a3 and a5 and a7 and a9 to be 0 as well, which we'll note when we get there. Now I can take the recurrence and I can plug r is equal to -2 into it to see what happens for all the rest of the terms. So you take r is equal to -2, you plug it in up here, and the thing that comes out the other side when you're all done simplifying looks like this. an is equal to -1 n minus 4 over n times n plus 1 an minus 2. That has an interesting property because this equation holds for n is equal to 2, 3, 4, 5, and so on. And we already know that when we put in 3, we're going to get a3 is equal to 0 because a1 was 0. So what happens with the even terms? Well, if you calculate a2, you can see that the 2 goes in here to replace the n. 2 minus 4 is -2. You cancel the negatives, you get 2 over 6, which is 1/3 a naught. But what happens at a4? Well, at a4, the 4 goes in for the n, and 4 minus 4 is 0. So that means a4 is 0 a2s, which is 0. But if a4 is 0, then a6 is 0, and a8 is 0, and a10 is 0. So this answer is actually just a polynomial. In fact, it's this polynomial. The x to the -2 is the x to the r1. And we have factored out the a naught, but this is just a naught, and that's a2x squared. You can see it right here. And that's it. Is that a Frobenius series? Yes, it is. It's an expression of the form x to the r times a power series. It's just not a very complicated power series. It's a polynomial. We're going to see something similar happen in the second solution. For the second solution to the equation, because we're dealing with an integer difference between r1 and r2, it's possible that the a inside this term may or may not be here. What do I mean by that? Well, if the recursion works, then I can use the recurrence relation to get a second solution, which will look like a Frobenius series. But if the recursion fails, that is, if the trouble term that we picked out earlier causes an inconsistent equation, then y2 of x will have a term attached to it that looks like y1 of x times the natural log of x, plus another chunk of a Frobenius series. And we have to check to see if this thing is here or not using the recurrence relation. So how do we do that? Well, now what we're going to do is we're going to plug r equals -3 into the recurrent structure that we had last time. And to emphasize the fact that we're dealing with y2 right now, we put b's into the recurrence. Okay, so here's what the recurrence looks like with the b's inside of it. And now we're going to take r is equal to -3 and plug it in, and we'll check all of the conditions on a naught and a1 and so on. When you put when you put r equals 3 into this n equals 0 piece right here, so this is equation 1 again, then you get 0 a naught is equal to 0. That's the result. And that means that, sorry, it's not supposed to be an A naught, it's supposed to be a B naught. And that means that B naught is arbitrary, right? If 0 times something is equal to 0, then B naught could be anything it wants to be. Now we're going to check the trouble term, because this is an equation involving B1. And remember that the integer difference was 1 between -2 and -3. So if there's going to be a problem, it's going to happen right here. When you plug in -3 to the equation for A1, so this is all equation 2. And you can see it right here. This is equation 2. So you take all of this and you set it equal to 0, and you plug in r is equal to -3. What happens? Well, you end up with the equation 0b1 is equal to 0. And that means that b1 is also arbitrary. b1 is not 0. b1 could be anything, because 0 times b1 is equal to 0 is a solution that, or is an equation that always has a solution for every value of b1. If it was the case that we ended up with something non-zero on the right-hand side, and that can happen, there could be other coefficients running around over there, then, so what I'm saying is if this had been non-zero, then we would have an inconsistent equation and the recurrence would have failed. But it is 0. So 0 times b1 requires that b1 be arbitrary. Well, that's weird, but that's what happens, right? So b1 and b0 are unrestricted choices. And so for the rest of the terms, we can plug in r is equal to -3 into the rest of the recurrence relation and reduce it algebraically. And I believe what we end up in that case is this. So that's the recurrence relation for all the rest of the terms. N is equal to 2, 3, 4, and so on. Remember, b0 and b1 are arbitrary. So now we can just start plugging in numbers. b2, you plug in, you get 3 over 2 times 1, b0. b3, you can do the same thing where you, somehow I've lost some numbers here, but this is supposed to be 3 times 2 on the bottom here, and equals this. b4, well, 4 minus 5b2, it's pretty easy to see that you end up with this. Once you do the algebra, this is supposed to be a 3 times 1 right here. b5 turns out to be, well, what's 5 minus 5? Just like in the previous solution, when you put 5 into the recurrence relation into the n right here, 5 minus 5 is 0. And so that means b5, which is 0b3, is 0. But if b5 is b0, then b7 is 0, and b9 is 0, and b11 is 0. So there's another sort of weird finite polynomial piece in the second solution where I can arbitrarily scale it by the number b1. And then the even terms, that is the b0 and the b2 and the b4 and the b6, turn into this infinite series right here. So all of this is an infinite series dictated by whatever value you choose for b0. But then there's this extra piece running around where you've got this polynomial that's part of the solution times some other arbitrary constant b1. Now, you can let b1 be equal to anything. It's convenient to let it be equal to b0 because then these two series kind of lump together. But I've separated them so you can see the oddness of this structure, right? That you have a power series bit out of infinite number of even terms added to a finite odd polynomial. So the solutions to these types of differential equations can be really strange when the roots disagree by an integer. The second problem I wanted to talk about was the problem from the slides. In this problem, what's going to happen is instead of having a y1 and a y2 that we can both get from the recurrence even when the roots differ by an integer, in this problem that fails. So in this problem, we're going to look at a specific case of example 11.5.3. So I chose a value to plug into 11.5.3 so that I could not have to deal with having a parameter gamma. In my YouTube lecture on this, I made a slight mistake where I put a wrong number in the recursion relation because I copied it straight from the book, and either I made an error or they did. So it's fixed in this discussion. So with the differential equation, x squared y double prime plus x times 1 plus 2xy prime minus a quarter times 1 minus 2xy, we can pick out p of x and q of x like usual. So p is 1 plus 2x and q is everything attached to the y, which means that p naught and q naught are easy to pick. And what we end up in this case is the initial equation collapses to r squared minus a quarter, and so we end up with roots that are 1/2 and minus 1/2. So again, we are in the case of an integer difference because there's a gap of 1. And so once again, if there's going to be a trouble term in this series, it's going to be b1. That's where the trouble will be if there's going to be trouble. We do the usual derivation of the recurrence relation by just plugging in all the pieces, collecting terms up, making the powers match. When you do that, what you end up with is a set of sums where the indices, 3 of the indices are 0 and 2 of them are 1 after the powers match. And that means you have to pull off the 0 terms. But that's it. And so, of course, all of this up here is just the initial equation. And the rest of the recursion looks like this. Well, now we can plug in r values, just like usual. And if we plug in r equals 1/2, we get a standard Frobenius series. You put it in, you can check to make sure that a naught was arbitrary, which it is because you get 0 a naught is equal to 0. And this time for n equals 1, we actually are going to use the formula from up here. If we put 1/2 into that formula and we do a whole bunch of algebra, it ends up collapsing to this. So that's the recurrence relation corresponding to r is equal to 1/2. All I've really done here is multiply things out. At one point, I decided I didn't want to deal with fractions, and so I sort of cheesed the problem by multiplying through by 4. So I put a 2 into here, and a 2 into here, and a 4 into this term, and a 4 right here, which is how you get this. And then you have to multiply through by 4 on the other side as well. And so I put one of the 2's into this 2, and another 2 inside here. That's that term multiplied by 4, and then the 4 hits this and turns it into a 2. So if you're curious how I made this leap right here, I just multiplied by 4 so that I could clear all the fractions out of the problem. Probably not worth the time it took, but that's what happened. Okay, so from there you just have the standard coefficient grind. You can, A1, A2, A3. We don't expect any problems for the first solution because we always know that we're going to have one Frobenius series solution. We've set up the method so that that always happens. Kind of an interesting pattern here where you have these like double factorials going on. Now for the second solution, again, it's the case that we have this a y1 natural log of x floating around out here. And I need to know if that's there or if it's not there. So I'm going to check the recursion. Here's the recursion from last time, right? The general recursion that we worked out is right here. And so what we're going to do is we're going to plug in r is equal to minus 1/2 and see what happens. So first we'll put r is equal to negative 1/2 into the initial equation part. And then we're going to, that's pretty easy to check is equal to 0. And then we're going to put it into the rest of it. So that's all of this. And that's what we did right here. So that's just the computation of taking everything inside the power series as the coefficient and plugging in r is equal to 1/2 into it. And when you do that and you reduce the recursion, what you end up with is something that looks like this. Now I want you to notice that I haven't divided both sides by n times n minus 1 yet, because there's no guarantee that that's not equal to 0. Where is the problem term in this problem? Well, the problem term is that n is equal to 1, because remember the roots were 1/2 and minus 1/2, and 1/2 minus minus 1/2 is 1. So that's my n value. So I'm going to plug in n equals 1 and see if the equation is good or bad. When you do that, when you put n equals 1 up in here to this recursion for the second solution, what you end up with is something that looks like 0a1 is equal to something that's not 0 times a naught. That's impossible. You can't have 0 times something is equal to something non-zero. Right? This equation is, even if a1 was 0, you still have an inconsistent equation because a0 is not 0. a0 is not equal to 0 by assumption. So that means that you can't use the recursion. The whole approach to the problem breaks. And that means you must include this y1x natural log of x term in the second solution. And so that means that the general form of the second solution is the ugly one. Okay, so hopefully that comparison of two problems of the same type that go different ways is a useful one. And where was the split in how these things acted? Well, when we looked at this equation right here, we ended up with something impossible. 0 times a1 is equal to something that's explicitly not 0, which can't happen. When we checked the other problem, we ended up with an equation that was consistent because 0b1 was equal to 0. So the actual recursion did not involve a non-zero earlier term. And that means that here we could select b1 to be anything that we wanted, which is why that carried through with the Frobenius series method, even if some of the terms stopped after a finite number of entries. Okay? All right, so if there are more questions along these lines, I would love to make more examples and to talk about them. I hope this is helpful. Let me know if you need more. Let me know if this was helpful, and I'll talk to you guys later.